and welcome to MN 234. This is the review for the final exam for metallurgy. The goal of this lecture is to go through the metallurgy review PowerPoint, which is all of the PowerPoints that we've looked at up to this point. I just shoved them into one folder or one PowerPoint anyways, and I didn't clean it up, so it's a little bit messy, meaning the format is not clean, which you'll see that when we flip through it. So the other thing is I'm going to give you a bunch of tabs, pages to tab, topics to review and understand. There will be some application questions on the exam, just like there was on the midterm, meaning that using the iron carbon phase diagram, if I give you a steel and I heated it to a temperature and I cooled it at a certain rate, what is the microstructure going to be? So there'll be some questions like that. So we'll look at the iron carbon phase diagram, just kind of a little bit of everything. But I'm going to go through this PowerPoint, which is 96 slides or something like that, and which seems like a lot, but we've already went through every one of these slides throughout the semester. So as you can see, I'm just kind of rolling down through some of these things. When I'm going through the review, I'm going to say that's not on the exam. I'm not going to ask you about hypo, eutectoid, and hyper-eutectoid. It's right on the bottom of the iron carbon phase diagram right here. So I am not going to ask you about that. There will be some other things like the isothermal transformation diagrams are not on the exam. So there'll be things that I'm saying this is not on the exam, and there's things that I'm going to say that, you know, make sure that you understand how to use this, because this will be on the exam. So that's kind of the goal, is to give you a more precise idea of what to expect on the exam, what topics, and pages to tab in your book, along with all of the other pages that I've told you through the semester to tab. But I'm hopefully should get to all of the pages that you should tab in your book that will significantly help you find things. Like page 25 is rolling direction. There was questions on the midterm about that. There'll be questions on the final about that. So kind of rehashing everything as I go down through there. I will be posting a separate audio of the format of the final exam and how that's going to go. So what to expect as far as the test taking. Obviously it's going to be open book, it's going to be online, but I will have a separate audio outlining more information on that. Metallurgy, the study of metals, going back to page 1 in our textbook. Early on in the chapter 1, it talked about different types of metallurgy: extractive, mechanical, physical, and welding metallurgy. I might ask about the definition of metallurgy, but not each of those individually. Everything on this page right here, understanding the terms of metals, alloys, ferrous, non-ferrous, and then especially chemical analysis, knowing what each of those are is very important, because as you read through the questions, these will be terms that we'll be using, and you got to be able to understand these terms to be able to understand the question. I might note, we talked about temperatures and changing temperatures from Fahrenheit to Celsius and Rankine, and there will be no conversions on the exam. You will not need a calculator. I did give you some numbers for density. I won't ask about those on the final exam, although they are good things to know. Melting points, we talked about melting ranges and understanding that there's a melting range instead of a melting point for most of the alloys that we're using will be helpful. Some more terms there. There are very few term questions on the exam because you can just open the back of the book and look at them under the index or glossary. So Very few, if any, definition type questions. Again, here we have temperature measurements. I think everybody knows what Celsius and Fahrenheit is. I won't be doing any conversions on the exam. Chapter 3, why do we do mechanical testing? That would be a good one to be able to answer. Knowing the types of loading, tension, compression, shear, torsion, and bending, on page 24 in your book. Be able to list them and understand what those are. And then on page 25 is rolling direction. I would definitely have that page tabbed. Remember, we talked about 3 rolling directions, right? There is longitudinal, transverse, and through thickness in that order. Longitudinal has the best percent elongation, the best fatigue life, and then transverse direction, which is perpendicular to longitudinal, that has the second best percent elongation and ductility and fatigue life, and then the through thickness, which is the thickness of the sheet or the plate that we're working with, in the Z direction. For those of you who do a lot of CNC work, the through thickness is the worst by far as far percent elongation and fatigue life and ductility. And in a lot of cases, we want to avoid putting our through thickness in tensile loading. Actually, in the welding code books, it's against the code to put plate, like steel plate, in through thickness tensile for a structural application. That's how bad it is compared to the other directions. So tab that page, be able to answer some questions about rolling direction. Reaction to forces, stress and strain. You should know those intimately. What is stress? What is strain? And then the stress strain curve. What does it represent? The stress strain curve really represents the mechanical properties of the part. I'll come back to the percent elongation. So when we look at a stress strain curve here, we have lots of information. The slope of this line right here, which you could do rise over run here, the slope of that line is the modulus of elasticity, which we didn't talk about, but you read about in the book. That is a mechanical property. We have the highest point on, I'm looking at this ductile curve here, the highest point on this ductile curve is the ultimate tensile strength. We have our breaking strength, our point of failure. We have our how much ductility we have by how far our component stretches or strains. We have, if I take the area under the curve here, this is the toughness of the material. So this really represents our mechanical properties. We can derive almost all, if not all, of our mechanical properties off from a good stress strain curve from a given piece of material. On page 28 in your book, it starts talking about toughness testing, which toughness is the area under the curve here. So know the difference between toughness and strength. When we're doing mechanical testing, how does our test conditions like temperature, environment, grain direction, which I just talked about a little bit on page 25 in your book, preparation of specimens, we talked about having nice clean surfaces and grinding marks and the surface finish, all makes a difference in how our part is going to fail. We talked about fatigue life. Fatigue life is the #1 failure of metals in service. That's the #1 reason why metals fail is through fatigue. So I mention that once in a while, like I said earlier, that the longitudinal direction is going to have better fatigue life, and then traverse, and then through thickness, which is not listed here or in the book, but we talked about it, we need to know about it. Our through thickness has the worst fatigue life. Why is that important? Because that's the number one reason why materials are going to fail. So when we design and build stuff, having that in mind, so knowing which of these directions we're loading the component in, or designing it so we're loading it more in our longitudinal direction than in the other two. If that's possible, that's what we want to do. So those are test conditions. Popular tests. Oops, too far. The tensile test, which yields the stress-strain curve, which is on page 34 and 35. You might tab those pages. Our tensile test yields our stress-strain curve, which gives us some points on the curve, gives us some information about the mechanical properties. I won't ask anything about guided bend tests. Hardness testing, we did hardness testing, and understanding the Rockwell scales. So we had HRB for softer materials, and we had HRC for harder materials. Chapter 11. Questions on making steel? No. Nothing there. So different levels of deoxidization. This understanding what these are here, not intimately, but killed and semi-killed are the important ones, because these are 99% of the materials that you guys are using are either killed or semi-killed. So just knowing the definition of those two levels of deoxidization. Nothing here. AISI steel designation, page 183 in your book. Definitely want to tab that page. There will be questions on identification. So I might give you something like 4140. I'm going to ask you 3 questions about that, right? I'm going to ask you the class or family, and I'm going to ask you alloy content, and I'm going to, which is going to be percent of each element, which is listed on page 183 in your book, and then I'm going to ask you carbon content. And that'll be a percentage also, right? So in 4140, we know that this is point. We know this is 0.40% carbon. Keep pressing buttons here. So these are the 3 things that I'm going to ask you, and there will be a couple questions about material designations off that page. Make sure that you tab that page for sure. Chapter 12, carbon steels, crystal structure. I would be able to list the common crystal structures that we talked about. Make sure that you understand the difference between crystal structure and microstructure. That's a huge problem on the tests. It was on the midterm for some of you, and it will be on the final for some of you, unfortunately. But make sure you know the difference between crystal structure and microstructure. Crystal structure is the atom arrangement, and microstructure is the phases. So looking at phase descriptions, these are on page 190 and 191 in your book. Know these definitions quite nicely. I will not ask, I already said I won't ask about these. They're on the iron carbon phase diagram. Critical temperatures. What are our critical temperatures? The lower critical temperature for all steels is 1333 degrees Fahrenheit, right? That's the horizontal line on the iron carbon phase diagram. And know what the upper critical temperature is by definition, not by temperature number, but by definition. And the upper critical temperatures are these two lines right here. There's the upper critical temperature, and there's the upper critical temperature. And it's where we go from the transition phases to austenite. The lower critical temperature is our 1333 line, which is right here, and that is where we go from perlitic to start getting austenitic, or vice versa. That's where the austenite zones end and the perlite or perlitic zones, which is all of this down here, begin. So a little review of the iron carbon phase diagram. We have on the left hand side over here, we have temperature in degrees Fahrenheit. On the horizontal down here, we have carbon content. So this is percent carbon down here. And so this is 0.5% carbon, 0.8% carbon, and 2% carbon. So if we're talking about steels, we're only concerned up to 2%, right? And for the most part, I've been talking, we're really only concerned up to about 2,000 degrees. There are very little heat treatments that we do that are above 2,000 degrees. So if we just look at this bottom left-hand corner of our chart, now this over here on the left-hand side, we're going to forget about that because that is, see the little A right there, that up here in our key right here, that is ferrite. Pure ferrite is not steel because steel is an iron carbon alloy. So I got to get rid of my carbon for it to be ferrite down here. This is essentially not steel. So forget about that. Just forget about it. It's not even there. So really we have 6 zones, right? And I'm going to start in this bottom left-hand corner. We have perlite and ferrite. Here we have ferrite and austenite. That's what our ferrite and austenite. We have austenite in this zone up here. We have austenite and cementite here, which comes from that. And then we have perlite and cementite in this zone right here. And then right here on this line, we have, right here, we have 100% perlite. So we have 1, 2, 3, 4, 5, 6 zones. That's this zone right here. There's number 6. It's right on that line. So it's not, I know a line does not have any area, but that line right there, theoretically, if we landed right on that line, we'd be at 100% perlite. So that's 6 zones. And that's really how we want to look at this iron carbon phase diagram. So this horizontal line right here, which is our lower critical temperature, is a divider. This vertical line right here at 0.8% carbon content is a divider. And then we have our upper critical temperature as our other divider. Let me clean this up a little bit. So I have highlighted the 4 zones right here. So we'll start again. So, and the number order doesn't matter. I'm just counting zones here. So we have perlite and ferrite, which is in the red area, which is zone 1. We have ferrite and austenite, which is in the green area, which is number 2. We have austenite, which is this other blue area, the darker blue, that's area 3. We have this mustard zone over here, yellow, which is our austenite and cementite. Forget about the lead bright, we don't care about that right now. Just austenite and cementite, that's area 4. We have perlite and cementite, which is area 5. And then we have the purple line right here, which is area 6. So those are our 6 zones. So how do we use the iron carbon phase diagram? Let's pick a material for an example here. Let's 4140. For those of you in the machine tool industry, that's a familiar material. So we know that this has 0.4% carbon in it. So we're going to come over here at 0.4% and we're going to draw a vertical line that's relatively straight. And I'm going to say we're going to heat this to 1800 degrees, might be a bit hot, and then quench. No, I'm going to say we're going to heat it to 1800 degrees and then we're going to slow cool. So what is my microstructure going to be? Well, at 4140, I got 0.4% carbon content, and I'm going to heat it up to 1800 degrees, which is right here, which would be austenite, but I'm going to slow cool it. So this diagram only applies to slow cooling. So when I cool that down and I get down to room temperature down right here, what is my microstructure going to be? Well, I'm in that red zone. So it's going to be perlite and ferrite. What was it when I was at 1800? Well, at 1800, I'm right here on that line, and I'm austenite. So I could have asked two things here. I got a piece of 4140, I've heated to 1800 degrees, what is my microstructure? It's austenite at 1800 degrees. If I slow cooled it, which means down to room temperature, I'm going to be perlite and ferrite. So I need a carbon content. I'm going to plot my carbon content, and I need a temperature. So I can plot that on my diagram. Another example, let's say we have a 1090 steel and I'm going to heat that to 1750. What is my microstructure? Well, I got 0.9% carbon content, so I'm going to come over here and I'm going to draw a vertical line at 0.9%, and I'm heating to 1750 degrees Fahrenheit. So over here at 1750, there's my temperature. So there's my microstructure right there. So at 1750, my 1090 is going to be austenite. If I slow cooled that down to room temperature, I'm going to be down here, which is going to be perlite and cementite. So I could have asked either one of those questions. What if I heat my 1090 to 1750, I'll be at austenite, and then I quench it? What's my microstructure going to be? It's not on this diagram, is it? Because the diagram only applies to slow cooling. If I quench austenite, I'm always going to get martensite. This iron carbon phase diagram will be available to you. It's on Blackboard, but I will have it available to you for the exam. Mechanical properties. How does perlite interlamellar spacing, how does grain size, how does grain direction, how do those properties affect ductility, primarily ductility? How does grain size affect ductility? Remember, fine is small grain and coarse is large grain. We know that finer grain size increases ductility and coarser grain size reduces ductility. Same thing up here. Finer perlite lamellar spacing will increase ductility and toughness. Coarser will reduce ductility. Chapter 13, cooling rates and hardenability. Remember we talked about this opening paragraph right here, which is on page 193 in your book, the austenite transformation products. You should know what that means. What is an austenite transformation product? That means that we have our steel and it is heated up above our upper critical temperature. If I draw the iron carbon diagram up here, so we have austenite up here, austenite symbol. So we're in this zone somewhere. We're in this austenite zone. So when I cool this down out of this zone, if I cool it slow, it's going to follow the iron carbon phase diagram. But if I cool it fast, it's not. It's going to turn into either martensite or bainite. So when we say austenite transformation products, you should know what that means. We've austenized and we're going to cool it and it's going to turn into something else. That's what that means. Hardenability And hardness, we'll come back to this here in the Chapter 13 review, but know the difference between hardness and hardenability. Know that difference. People get that mixed up all the time. So we look at cooling rate two different ways. Cooling rate is a way to measure a quantitative value in degrees per second, and I use a lot of times, I'll use the nominal terms of fast and slow. And fast means that we are quenching and we're going to form martensite or bainite if noted. And slow means that we're going to form pearlitic products. But one, say degrees per second, let's say we're at 350 degrees per second. For one material that may be fast, and 350 degrees per second for another material might be slow. So this is a cooling rate is a quantitative measure. These tell us whether we're going to end up with martensitic products or pearlitic products. Know what our pearlitic products are. The definitions of these are on 190 and 191. And then martensite, which is body-centered tetragonal, BCT. And know what martensite is. Know how we form martensite. The only way to form martensite is to austenize our material and then do fast cooling. If you remember on the board, on the whiteboard, I had my diagram here. My little diagram right here. We have pearlitic products down here. We have austenite at our elevated temperatures. So this is on heating, the red line, red for hot. So if I take my perlite and I heat it up, it turns into austenite. And if I fast cool it, over here, fast, and this is slow side. If I fast cool it, it's going to get into martensite. And if I take martensite and I heat it up into austenite and I slow cool it, that's how I get in perlite. Notice that there are no horizontal lines. There's no way I can go from pearlitic products to my martensitic products. And over here on my pearlitic products, I have perlite and ferrite, full perlite, and perlite and cementite. It doesn't matter what type of steel it is. When I slow cool it, it's going to be pearlitic. If I fast cool it, it's going to be martensitic. Now I usually put bainite over here in parentheses because that's more of an intermediate cooling rate, but I have to austenize and I got to cool at the appropriate rate, which is going to be fast comparably to get my bainite. So if I quench it, I'm going to end up with martensite. If I slow cool it, I'm going to end up with pearlitic products. So this is kind of for all steels. This is how I get from pearlitic products to martensitic. I got to go through austenite. And vice versa. If I have martensite and I heat it up to 1800 degrees, it's going to be austenite. And then if I slow cool it, I'm going to be back into pearlitic products. If I take martensite and I austenize it at 1800 degrees and I quench it again, I'm going to end back up in my martensite. If I couple that diagram with the iron carbon phase diagram, so I said 1800 degrees and I said I'm going to be martensite, because pretty much for all steels until I get somewhere over here in 1.75% carbon or greater, except for this area over in here, at 1800 degrees I'm going to be austenite. So if I quench austenite, I'm going to be martensite, which is not on this diagram. But if I slow cool it, I'm going to be down here in my pearlitic products. So that's kind of the gist of what this iron carbon phase diagram tells us and what this diagram down here kind of gives us information for. So austenite transformation products, they are going to be either pearlitic or martensitic, or intermediate cooling would be bainitic. Now we didn't talk a lot about bainitic products, and if I am asking a question about bainite on the final exam, it will be explicit that I will be talking about bainite. I will say bainite in the question. So really we're more concerned about pearlitic products and martensitic products. Bainite is used, but it's a small percentage. No questions on this stuff here, unless you are in a quality situation or an engineering situation where you are doing cut and etch and looking at microstructure. Only then would you need to know the difference between plate and lath and mixed. It's just an appearance thing. It's not a property thing. Bainite, like I just said, if I ask any questions about bainite, it will be explicit in the question. The isothermal transformation diagrams, they will not be on the exam, but what we do need to know about them is what happens. So the isothermal transformation diagram, we have temperature on the vertical, we have time on the horizontal, and so we are starting at high temperatures because we're austenizing material, because this is all about cooling, because it's about austenite transformation products. So we're starting out as austenite, which is at an elevated temperature, and we are cooling at some rate. And if I cool like this right here, I'm going to end up over here and I'm going to form bainite. If I start over here and I cool very fast like this, I'm going to end up with martensite. If I cool really slow and I end up over here, I'm going to end up with perlitic ring. Those are my three finished products. Remember on the diagram, this black line here on the right hand side is my finished boundary, and this black line on the left hand side is my start boundary. And so this is my start boundary here, this is my finished boundary. So what that means is everything that's to the left, which I'm going to dirty up the diagram, everything over here is still austenite, untransformed austenite. So when I start up here at high temperatures, I am austenite, and I stay, even though I'm cooling down, and if I'm holding like this here, like in molten salt, I'm still austenite, even though, because this is a lower critical temperature, which means this line right here is 1333. Even though I'm below that, at this temperature right here, even though I'm below that, I am still austenite because I have not allowed enough time for transformation to take place. So when I cross this start line, I'm starting to form martensite, I am finished making martensite. So my start boundary, finish boundary. So what is important about this diagram? Slow cooling produces perlitic products. Fast cooling produces martensite. That's it. So if I quench, I'm going to form martensite. If I slow cool, I'm going to form perlitic products. And then intermediate cooling rates, and I have to hold it to get to bainite. So we don't have to memorize the diagram. We just got to know those three things. So over here, slow is perlitic products, fast is martensite. And we talked about cooling rates, degrees per second. I don't care what the degrees per second is. If it is slow, you have perlite. If it is fast, you have martensite. Or look at it the other way. If I take an austenized steel and I cool it and I end up with martensite, I cooled it fast or quenched it. For example, A2, a air quenched tool steel. This is a cold work tool steel, by the way. So if I take A2 and I austenize it, so I'm up here in my diagram, and I pull it out of the oven and I set it on the bench. Is that fast or slow? Well, it might be 50 degrees per second. Well, that end product is going to be martensite. So we would have to classify that as fast because we ended up with martensite. What if I took a piece of 4130 alloy steel and I austenized it and I pulled it out of the oven and set it on the bench right next to my A2? My A2, I just said, pulling it out of the oven and air cooling it is going to be fast because I end up with martensite. If I do exactly the same thing with my 4130, I'm going to end up with pearlitic products, and it's going to be way out here. So what is fast for one material might be slow for another material. So fast and slow is determined by its end product. Fast is the same thing as quench. So the CT diagrams, pretty much the same information as what we have on this diagram. So no questions off from that. What does all this mean? Charts show us how fast a material needs to be cooled to form each transformation product. Remember, this chapter is about austenite transformation products. How do you end up with pearlitic products? How do you end up with magnetic products? And how do you end up with martensite? Moving on to the second part of this chapter, which is hardenability. Know the definitions of hardness and hardenability. Understand the difference. Hardenability is a physical property. Hardness is a mechanical property. That's that's the big difference between them. Hardenability is the depth of hardening, or the depth of martensite that we get on a steel. For example, if I had a big block of A2 and I harden this, I'm going to get martensite all the way to the center. But if I had a big block of O1, I might only get hardening in this depth right here. So this out here is going to be martensite, and everything in the middle is going to be pearlitic products, because O1 doesn't have as good hardenability. Hardness, realistically, after tempering, if I tempered this one at high temperature and tempered this one at low temperature, I could end up with the same exact hardness, but they have different hardenability. So hardness is resistance to indentation. Hardenability is the depth of hardness obtainable on any given material.